Hi everyone, I'm Amanda, as mentioned by Regia. I'm a researcher at Wetsus. We are a research institute in the northern part of the Netherlands. And today I'm happy to share with you a little bit our experience with combining the research between academia and also industry in related to PFAS. And go, Gabriel.
Thanks, Amanda. My name is Gabriel Sigmund. I indeed work at Wageningen University as an assistant professor. My work very often involves persistent and mobile compounds. PFAS are, of course, the poster child for extreme persistence. Some of them are very mobile, so that's my role here. I work in the environmental technology department, but I also occasionally deviate from technology stream into the science policy and the environmental phase. I have many hobbies. And that brings me to my first slide. So those three images are not completely randomly put on this slide. You can see the first one is a seemingly pristine picture of an environment, an aqueous environment. Then we have an industry picture, and to the right, we have an agricultural image. And probably most people would link PFAS, at least to some degree, to industry activities, and maybe lately also a bit to the environment. And I would like to additionally highlight the agricultural sector as an additional source, as we will discover along today's seminar. But before that, even though we all pretend to know what PFAS are, let's just make sure we're all on the same page. So there are a number of different definitions for PFAS that have been established over the last, let's say, decade or over a decade. Personally, I think the most solid, most sound, and most chemically true definition was provided by the OECD. And that is basically that any compound that has at least one fully fluorinated carbon that is linked to another carbon is a PFAS. And I'm saying this because right now there are efforts to change this definition, particularly for the fluoropolymers, so for plastics and those kind of materials that are, for example, used in car batteries, as well as TFA, which will also be something that will accompany us through the first couple of slides. So we can share those slides if there is interest afterwards. I think, well, this is basically the OECD definition. So fully fluorinated methyl or methylene carbon atom without any weird stuff hanging around. Okay, so those are PFAS. And why are they so exciting, and why are so many people now concerned about them, but maybe 2 decades ago super enthusiastic about them? First of all, they're a universe of compounds, so there's no one feature that one could nail down, except for this fluorine-carbon bond being extremely stable. And this very high stability results in a number of very useful features. So those very stable compounds have been and are still used in basically an almost infinite amount of applications, because they're thermally very stable, and depending on their chain length, on their molecular features, they can repel both water and oil. So if you think about frying pans, outdoor jackets, and whatnot, you all know this, of course, but I'm just kind of trying to get us all on the same page. All of those properties are related to this very, very stable carbon-fluorine bond, because that moiety is super stable, does not break down, but this also means that moiety does not really interact with other stuff. So if you want to have an inert surface, say for a medical device, for frying your vegan burgers, or for going outdoors without rain and or oil getting through your jacket, those are perfect, because they don't really interact with anything, because they're happy with the carbon that they have, those fluorine atoms. That's kind of the state of things, that PFAS are more or less, or have been more or less used everywhere. And it has only been about, let's say, 5, being generous, 10 years that some industries have started to phase out completely from those polyfluorinated compounds. I would say up until 5 to 10 years ago, the more famous bad boys were just replaced with a less famous PFAS molecule that had basically similar properties, which of course results in similar issues and problems. So PFAS at least some PFAS are documented to be endocrine disruptors. Some have been associated with cancer. Some have been associated with decreased immune responses, and there are basically a whole range of effects that are not super duper easy to measure. So from an ecotoxicological point of view, those effects that PFAS induce are typically not your I'm killing all the fish immediately, but it's rather something a little bit more subtle that is also harder to measure. Of course, if you put enough of them in, you will kill your fish immediately, but generally that's not what's happening. Okay, that being said, now we know PFAS are everywhere. They've been used a bunch. They have those properties that are super useful from a technical point of view, and they may cause some harm. Sorry. So what about their behavior in the environment? How do they move around? Where do they stick? Where do they not stick? Well, because generally speaking, at least let's say our most common PFAS molecules have this fluorinated carbon chain length. I don't know if you can see my mouse. Let me find.
Yes, we can see.
Oh, you can see my mouse. Great. So you have those fluorinated carbon chain lengths, and then at the head, usually you have a negatively charged functional group. So this might be a carboxylic acid or a sulfonic acid group. So P4 and PFOS are probably the most famous examples. And if we think about the environment as a whole, if we think about topsoils, something like, I don't know, 95, 97% of topsoil surfaces are negatively charged. Organic matter is negatively charged. So even if you have some goethite or some bits of positively charged things in that soil, the organic matter will immediately cover it. So practically, we can assume topsoils to basically always be negatively charged. And this, of course, means that if you have a PFAS molecule that is also negatively charged, it will be repulsed from most surfaces and thereby become more mobile than it would be otherwise. Now, that's the head part of the PFAS, so the bubbles on the left. Depending on the chain length of the PFAS, they have a more or less hydrophobic tail. So for long-chain PFASs, this tail basically makes them surfactants. And surfactants have a very interesting profile that if you assemble high enough concentrations in water, they will self-assemble. They will basically form micelles and party together. At slightly lower concentrations, if you have a porous media, let's say like an activated carbon, they might still assemble and form hemimicelles. Now, this is all driven by hydrophobicity, so it's not a specific interaction. It's just an effect of entropy, basically, right? If we look at more engineered adsorbents, such as, for instance, anion exchange resins, those have a bunch of positively charged surface sites. There, you might have basically an interaction both from an electrostatic interaction point of view, as well as this kind of micelle formation. And this makes describing their behavior quite complicated because you basically have a process that is driven by electrostatic interactions and a bit of hydrophobic effects at the lower concentration end. And if you increase in concentrations at some point, those surfactant-like behaviors become more important. So this means to describe PFAS adsorption across concentrations often is quite a challenge. To make things more complicated, because they're not complicated enough, all the other stuff that is in your water will change this. So you can imagine if you have a negatively charged PFAS and you have a lot of positively charged ions like magnesium or calcium, those would kind of buffer the electrostatic interactions down. So they would decrease the electrical double layer around negatively charged surfaces, and they could even, if they're divalent, form cation bridges, as shown here in the lower figure C. So all of that being said, what we generally do know about PFAS mobility and sorption is that the longer the chain is, the more you have this issue of hydrophobic interactions or hydrophobic effects. I personally prefer to say effects than interaction. We can discuss why later. And the smaller your chain length gets, the more this is driven exclusively by the electrostatic effects, which means if we look at, if I could click. if we look at our most extreme example, this is TFA, perfluoroacetic acid. This is the smallest PFAS that we know of. It has 2 carbon atoms, it has this fully fluorinated end, and it's fully negatively charged basically at any pH. This guy does not stick anywhere. It will not break down because we are just discussed that those fluorine carbon bonds don't break down. The carboxylic acid is the most oxidized state this molecule will be at. This guy will not break down and not stick anywhere. So this is an environmental scientist and an environmental engineer's nightmare. It's super small, super mobile, super persistent. And now comes the big additional complicating factor about TFA. TFA generally is not directly produced and used by industry. Generally, TFA is a transformation product from other stuff. And you might be surprised, back in 1993, so quite a while ago, the formation of TFA was already documented in the scientific literature. So this was basically because of the Montreal Protocol, because of the ban of chlorofluorocarbons, because of the ozone layer depletion. Fluorinated compounds were used instead of chlorinated compounds. And well, one of the most popular ones, the one shown here, HFC 134A, was already documented to form TFA back in 1993. And of course, since then, many people have worked on this issue. I have to say there was kind of a peak on this work in the 90s, and then in the 2000s, everyone forgot about it. And let's say around the 2010s or so, people started to get interested again. We now know that using those refrigerants, those cooling agents, those replacement molecules that did save our ozone layer probably is a major cause for a bunch of TFA formation in the atmosphere that is now globally distributed. Wherever you take a rain sample, Ian Cousins and colleagues showed this, I think, 1 or 2 years ago. Wherever you take a rain sample, you will find some TFA in that rain. This means TFA is now globally distributed. It's everywhere. There's no way we're getting completely rid of it. So some people argue, and I would be part of those people, that with TFA, we have exceeded the planetary boundary. So I would say if we cannot go back, this is a boundary that we should not cross. And with TFA, we definitely already crossed this boundary because there's no way we're going back. TFA is everywhere, and it's almost impossible to get it out everywhere. That being said, because I know you're all bored and it's all so simple, let's make our lives a little more complicated. TFA is not only in those kinds of agents, it's also super popular as a fluorinated carbon side chain in a bunch of pesticides. So last year, with a bunch of colleagues, we tried to make some estimates on TFA formation rates based on pesticide application rates that are estimated for, in this case, Europe, but we also did the same exercise for the US. And there's a big uncertainty related to this figure because industry and researchers barely report or know, in this case of researchers, how quickly, how much TFA is formed from those pesticides that have this side chain. But the few reported numbers range from somewhere between, let's say, close to nothing to 80–90%. And I would argue the close to nothing is probably an analytical issue and not so much a fundamental issue, but that's a different story. But what we show here, or what we estimated here, is that in a bunch of regions, TFA from agricultural residues, basically, from pesticide use, may be a substantial source to groundwater pollution. And to not just keep it as an academic kind of data-driven voodoo exercise, we actually got a bunch of data from a region in Germany that did very highly resolved monitoring of groundwater. And then in that region, we tried to assign agricultural landscapes to non-agricultural landscapes and compare them. And that's this figure here. Those are real data with hundreds of field measurements. On the left, you can see the official categorization of agricultural land use versus non-agricultural land use. Although those data are a bit sketchy and not complete, I would say. So the left side is like, but still we already see quite an increase in PFA concentrations really measured in groundwater and aquifers. But if we go from left to right, where we use the nitrate concentrations in the aquifer as a proxy for agricultural activity, which I would argue is very fair to do, you can really see that the concentrations of DFA measured in those aquifers are 2 to 4 times higher than in the non-agricultural fields. So agriculture really is a substantial contributor to TFA right now. And here comes now the really scary part. As we don't know the formation rates, but we do know those pesticides are out there, we don't know how much is still to come. Because even if we stopped using any polyfluorinated pesticide right now, it would take several years at least for all of them to completely degrade. And only then would we know how much is already out there, right? So this is kind of quite concerning, I would say, at least to me. And now I will try to convince you why it should be concerning. So if we think about the water cycle, sometime in school, we all saw an image like this one or a similar one. It's all connected, right? This is not just an esoteric saying. Well, the water cycle is actually all connected. It does not see borders. It does not see nations, races, wars. It does not care. Water just goes wherever it wants to go. And usually it is cycled. So it evaporates, the vapor is transported, somewhere it rains, it runs off, some of it infiltrates into the groundwater, some of it stays in the rivers and goes to the oceans. As I just mentioned earlier, for TFA, we already know that it's in the rainwater everywhere. This may be true for a number of PFASs, especially the short chain ones that are very mobile. So this, I would argue, is a really big reason to be worried if we want to protect our water resources in any shape or form. Because if we cannot go back, this means we have to treat all of this stuff forever, which is a bit of a pain. To make this point a bit more quantitative, some colleagues around Hans-Peter A. and Jianyun Wang, they and Ian Cousins, they compiled data from the published literature. This was more or less at the same time as we published our agricultural paper. And what you can see here is the reported median and maximum values in all different types of compartments. In the rain, in the rivers, in the lakes, in the ocean, in ice cores, in groundwater, all over the place. And what you can generally see is that the green bars are generally lower than the red bars. Of course, the sample size is not very big, but this trend is consistent almost for all compartments. And what this means is that the overall concentration of DFA has increased quite substantially all over the place. Confirming what I said earlier. It's in there. It will keep being formed by all of those different types of precursors. And we have a problem, so to say. Okay, that being said, we're all solution-oriented, happy people. So if you would talk to a less cynical student compared to myself, you would say, what do we do? The very obvious answer is nature is the solution. Kumbaya. Let biodegradation and natural attenuation do their jobs. There have been a bunch of attempts at this, but I have bad news for you. The number of solid evidence that PFAS can actually be biodegraded is none. And people have been working on this for a number of years now. So we can somewhat safely assume under normal conditions, I'm not talking about maybe some volcanic extreme acid volcano drain where you throw some PFAS in at 900 degrees, well, it will degrade there. But let's say in the overall environment, PFAS will not degrade, at least not the fully fluorinated ones. The ones that are partially fluorinated will degrade into smaller compounds that then don't degrade. That's what the TFA example just was about, right? So what does this mean? It means that our biological treatments, so our wastewater treatment plants, but also all kinds of other biological treatments that we may or may not have in place, the only thing they will do is that they will separate some of the longer chain PFASs into their sludge, and they may or may not degrade some of the precursors to shorter chain PFASs that are harder to remove physically, right? Because they're small, they're usually negatively charged, they're a pain. So biology is unfortunately not the answer. That was plan A. So let's go to plan B, separation. Yeah, I think last year with some colleagues, we compiled a mountain of data from all kinds of studies looking at PFAS absorption to, let's say, more or less commonly known and used adsorbent types. And I will kind of specify this a bit in a second, but just for you to know, basically all of the black dots are activated carbons or biochars or some kind of carbonaceous material. All the red symbols are polymer-based adsorbents. So this is your ion exchange resins, for instance. All the green ones are different types of cyclodextrins. And the yellow ones are basically zeolites and mineral organic frameworks. And what you can see here, generally speaking, in this circle, if we go from the top clockwise downstairs and back up, we basically have the number of fully fluorinated carbon atoms listed here. So TFA would be here at the number 1, and then we kind of go upwards. And you can see that going from the center to the outwards, we have an increase in sorption affinity and sorption capacity. And you can see that basically at those very, very small molecular sizes, absorption is really, really bad for almost all of the materials. You have a few ones that are okay-ish, but generally speaking, sorption is not a very good option. And around 4 or so fully fluorinated carbon atoms, we can see that for the carbons, as well as for some of the cyclodextrins, the performance kind of increases. And it's decently good up until a chain length of 8 to 9 fully fluorinated carbon atoms. And the reason why it's not as awesome beyond that is that those very large molecules don't really fit into the meso and micropores of your activated carbon and your biochars. So they're sterically hindered. And on top of that, they will tend to stick to other stuff as well. So there's kind of an upper cutoff as well on what we can remove really well from water in a targeted manner, at least. And what is also quite interesting is that you can see that this median line, this black dotted line, generally, this is kind of your traditional carbon materials. Well, it's tailored carbon materials for PFAS removal, but still, those carbon materials generally still do a decently good job. They are here and there, they're outperformed by cyclodextrins and the one or the other zeolite maybe, but generally they're doing very well. So everything is good and well, and we're all happy. We can go home, take a break, and celebrate life. Unfortunately, all of those studies were conducted in very clean environments. So basically in pure water, maybe a bit of salt here and there, a bit of calcium chloride perhaps. If we would have such a picture for, let's say, a wastewater treatment plant effluent, I predict that this image would look very differently. Unfortunately, we don't have those data to create such an image because, of course, there are documented experiments and sorption experiments with real matrices and with effluents and whatnot, but those are so different and in number much, much smaller than those experiments that I'm showing you here. So right now, it's kind of a bit unclear what really is the overall trend. Personally, I would assume that some specific tailored sorbents like zeolites will eventually outperform the activated carbons just because the zeolites are more specific for small molecules and your organic matter that covers the activated carbon doesn't really cover the sorption sites in the zeolites, for example. But, and I have other thoughts on this and we can discuss this maybe later, but generally speaking, this is what we find in the lab, but we don't fully know how well we can translate this elsewhere. And on top of that, even if it works perfectly well, the PFAS are not destroyed, right? They're just separated. We still need to do something about this. So for activated carbon, regeneration happens at 800-900 degrees, so they are destroyed during regeneration. For many of the other sorbent types, you have different types of regeneration, like resins can often be regenerated using solvents. And then you have this solvent liquid with lots of PFAS in it that you do need to do something about, right? So this is an additional challenge that we need to face looking forward. Speaking of liquids with high concentration of PFAS, there's another way to create those, and that's membranes. So there are different types of membranes that have different size cutoffs. So nanofiltration and reverse osmosis are basically conceptually a very similar principle, it's driven by steric separation. So you have different pore size and you're pressing your liquid through. And then what remains, what is rejected, that's your concentrate stream that you do need to do something about. And then there's another kind of type of membranes that have larger pores but have somewhat absorptive properties. So they may have positively charged surface functional groups or other stuff there that may or may not remove some of the PFAS. What all of those membrane technologies have in common, though, is that, as I said earlier, they generate those concentrate streams. So they do need to be treated, they need to be destroyed. Which brings me to plan C. Why separate? Why not just destroy them in the first place, somewhere down in the aquifer where we do not need to worry about it? Let's just clean it all up. No, this is not a very interactive discussion, but I'm pretending to ask the audience, and I'll pretend to hear someone say, I'm not sure, but it seems like a lot of volume. And I would say that is precisely right. We cannot directly destroy PFAS in almost any circumstance because it would be so expensive to treat such large volumes, it's nearly impossible. This means the generalized master plan to deal with PFAS when they're out there is to detect them, adsorb them, or separate them with a membrane, and then find a way to degrade them. We first need to up-concentrate them before we can destroy them. Of course, this is only the first half of what we should be doing. I would argue at least as important is to restrict their use for all kinds of precursors and phase out and substitute them wherever possible immediately. And where it's not possible immediately because there's some kind of essential use, like in a medical device, we should really come up with a phase-out timeline and with finding good alternatives to those types of compounds. And I would really argue to stick to the OECD definition of PFAS and really be comprehensive about this. Because right now, there are some quite loud voices that, for example, claim that the fluoropolymers should not be considered as PFAS. Some claim that the TFA should not be considered as PFAS because, of course, it makes life easier for industry and for some other players. On the long run, it will not make anyone's life easier. Even your fluoropolymers that by themselves don't really pose a big risk, during production, they emit a bunch of PFAS. And almost more importantly, if you think about it in a global scale, not every country has super sophisticated, well-regulated waste management approaches, which means those fluoropolymers will be burnt in an uncontrolled manner all over the place, which, guess what, will form a bunch of new PFAS. So this is kind of my key message. Let's stick to this comprehensive understanding of what PFAS are, and let's keep in mind that basically all of those precursors that are already out there are very hard to grasp. So that's kind of may or may not be a ticking time bomb. We just don't know, but it's definitely something we should keep in mind, that just analyzing 5, 9, 20, whatever targeted PFAS may not be really comprehensive enough, which means we should also transition, also when we develop technologies, we should transition towards total organic fluorine mass balancing, really understand how much is in there overall. And with that link to technology development, I hand over to Amanda and stop sharing my screen.
Thank you, Gabriel. So allow me to continue the nice presentation that Gabriel gave. I hope I can match his energy with this sense. Let me share my screen. I think I need to share my whole screen. I hope you see the presentation file.
Yes.
Okay, thanks. So allow me to continue what Gabriel already said, that PFAS is not only the problem for one sectors. For example, it's not only the problem of the water sectors, but as you see, we can also limit the use of PFAS. So it can be also the problem of the technical companies with R&D, but also with the new regulation. For example, in the European wastewater directive, even though it's not put in there yet that we need to remove PFAS, but they ask us to follow and also to measure the PFAS in our water. It's also become attention for our end users. For example, in the water boards in the Netherlands, they were thinking what kind of technology should we apply in our wastewater to remove PFAS. And also in drinking water companies, for sure, with the strengthening regulation about PFAS, like 100 ppt in our drinking water, or 4 ppt even for 6 PFAS in the US EPA. It requires this company to find what is the best solution to remove PFAS from our water. So as also Gabriel mentioned, that there are a lot of knowledge being developed by the university. For example, he's looking at this how PFAS in water is, and also in groundwater, and also how it's related to agriculture. So how if we kind of like combine all of the knowledge that we have from the Knowledge Institute, and also the need or the opportunity that can be open for the technical companies, and also to help to solve the problem of the end users, we combine all of this knowledge together to tackle the PFAS. And not only about PFAS, that's what we are doing actually at Wetsus. So maybe for some of you just joined, Wetsus is a research institution located in the northern part of the Netherlands, where we combine the fundamental knowledge and the technological needs. And we are creating our research in multidisciplinary environment. So this is the picture on the right-hand side are the 20 research team that we have at Wetsus, where, for example, I'm interested about phosphate recovery. So actually there is also a specific team about phosphate recovery, where all of the PhD researchers, university supervisors, and also company members meeting together and build the knowledge on phosphate recovery. They make their new technology about phosphate recovery. And regarding PFAS, the PFAS research at Wetsus is spread across different teams because, as I mentioned previously, it's not only one sector or one company problem. So, for example, some PFAS projects are in four different research teams. For example, we make the technology for PFAS concentration step. So, for example, in advanced water treatment, we try to find the effectiveness of the foam fractionation process. So, to further concentrate PFAS, specifically the long chain ones, because it's working with the foam, so it's hydrophobic, will be the main driver for this technology. So that's why it's working much better for the long chain ones. And you can see below of the picture are the companies who are interested and invested in this kind of research because they found that this research is going to be beneficial for them. And also on the right-hand side, there's also technology in desalination and concentrates, where they are looking for in situ electrochemical regeneration to effectively concentrate short chain PFAS. So with this process, the aim is to regenerate the activated carbon that already loaded with PFAS. The first one is they try to remove the short chain ones because actually that's the one that can cause early breakthrough in the activated carbon process. As also Gabriel mentioned, for example, TFA. So for example, TFA cannot be absorbed anymore. We apply electrical current and then it's going to desorb the TFA ones so it can extending the bed life of the granular activated carbon itself. And you can see also below the companies who are invested in this technology and also interested with this kind of project. Another two projects that we have not only to concentrate the PFAS, that also we also have a destruction process, what we call as a chemical-free PFAS destruction processes. So the first one in the applied water physics. So in this team, they're playing with the physics, water physics, by knowing the characteristic of water, that they put the plasma discharge for PFAS defluorination. So they put the high voltage on the water, and then it will create a lot of radicals that can help to destroy the PFAS. And you can see again the companies who are interested with this project within the team. And the right-hand side is a vacuum UV PFAS reduction and oxidation process. It's within the priority compounds and virus control. And there's also a company that interested in this project. So you can see that one team can have many or a lot of companies, and some of them have less companies because it's depending on their interests, but also depending on where they're gonna be like in a conflict of interest. That's also that we're trying to not putting everything in one team. So saying that one, so there are already quite some PFAS research in different research team, but actually we just built a new integrated PFAS stream specifically focusing on PFAS problem, and we started that one in 2024. And the reason why we still need to have this integrated PFAS team, as you see before, the technology approaches that we develop in different teams is usually specifically related to the needs of the company. For example, I'm a company making a UV. So I'm interested with the VUV process. Meanwhile, in this integrated PFAS stream, we really want to see the chain of integrated PFAS treatment, as Gabriel said before, to detect it first, to concentrating it as much as possible, and then to destroying at the end. But the knowledge with the other in the other teams doesn't mean that we cannot use it across the Wetsus. At Wetsus, we also share the knowledge about the destruction process and also concentration step across the team. So in these teams, because it's a challenge for different sectors, we already accumulate and also ask some companies to join us in this formation of the team. For example, the Knowledge Institute, we have TU of Eindhoven, Wageningen, and also University of Twente. And technical companies with R&D, for example, with Van Boos, is a technological company in the Netherlands. Murata is a company in Japan. They make a semiconductor. We have a Chemira chemical synthesis company, and we have also Aquacare, who can make a scale up of technology, usually an adsorbent. And then we also have end users who are interested with the project. For example, Vivens, water company who make a clean water for drinking water. Watercra is a consortium of 5 water boards in the Netherlands. Water boards are the people who deal with our wastewater. And also we have HVC, or a company who treat the sludge in the Netherlands. So with this team, we are working together and create some projects that we are thinking that interested for all of the company members. So that's why we have this dedicated integrated PFAS treatment team that with these 3 main aims. The first one is to make adsorbents that capable to concentrate PFAS million or trillion times. Because if we talk about activated carbon, it can concentrate PFAS up to 10 to power 4 or 10 to power 5 at the best scenario. And for membrane, it's only like a 5 or 10 times that we can concentrate PFAS. And then once we have the adsorbent, we need technology. We want to put it into a technology with a higher contact area than a pack bed, because the pack bed usually controlled by diffusion. It's required a longer contact time. So we are thinking whether we have a platform, whether we can have a platform technology where we can put this adsorbent and can absorb PFAS as much as possible. And at the end, for sure, we will also want to find a technology to destroy concentrated PFAS, either in the regenerant solution or, for example, in the sludge with minimal environmental impacts. With these 3 main aims, we come with 3 main projects. The first one, we make a novel adsorbent, what we call as a pillar urine, with the high capacity adsorbent for PFAS removal, and it's already patented. The molecule itself was developed by Professor Hans Salhoff from Wageningen University. And then about the novel process design, we creating a membrane adsorber with a high throughput that capable for current and novel adsorbent. And with this, we're working together with TU Eindhoven, with the Kitty Nijmeijer group. And the last one is the novel destruction process, because we know that PFAS could be also in soil and also could be in the sludge. We need to think about it, where should it go? So we were thinking about thermochemical destruction process with relatively low temperature. And with this, we're working together with the University of Twente, with the Professor Sasha Kirsten group about this destruction process. And I just want to show you a little bit about the patented technology that currently we have in the team. It's about the PFAS concentration step via adsorption. This is the molecule, what we call as a pillar urine. So it's like a benzene group that connected 5 of them, creating a ring. And this ring has a tail with ammonium tail on the top with positively charged. Initially, we thought that the PFAS will go to the inside of the ring, just like cyclodextrin, with initial complexation of 1 to 1. So 1 pillarine can absorb 1 PFAS. But in reality, we found that 1 molecule of pillarine can absorb 10 molecules of PFAS, because the PFAS will interact with electrostatic interaction, as Gabriel previously mentioned, because the positively charged of ammonium group on the top, and also the head part of the PFAS, which are mostly in negatively charged, will interact with that ammonium group. And similarly, because of the alignment of this PFAS, it's creating like a pillar, and then it's creating like a fluorophase, where this fluorine phase can attract another fluorine phase. So that's why we found that this technology can absorb quite a lot of PFAS from water. And that's mostly from me and Gabriel, and happy to discuss more and also for your input from our presentation. Thank you.